Hey everyone, my name is Mohammed Fahd Abrah, 17 years old. I proudly come from Yemen. I started my journey in programming when I was in intermediate school, and since then I've been on a mission to turn curiosity into real world projects. I learned several web development languages like HTML, CSS, JavaScript, PHP, and SQL. And I earned several certifications from freeCodeCamp. In fact, I built my own learning platform called Programming Ocean Academy. By the time I reached high school, I turned my career and my passion towards data science, machine learning, and deep learning, and I earned several certificates from IBM in data science, data analysis, data engineering, and AI engineering. And also, I learned several libraries in Python that serves data science and machine learning. For example, NumPy, Pandas, Matplotlib, Seaborn, Scikit-learn, Keras, TensorFlow, and Pytorch. In this video, I'll walk you through a beginner-friendly project which involves training a neural network on the FashionMnist dataset, training the model, evaluating the model, and making predictions on unseen data. So, regardless what age you are, this video will guide you through this beginner friendly project, and this video is a message to young learners, to young people. You can learn machine learning, you can learn deep learning, you can dive into the world of data science. These kind of messages, I want to send it to young learners, to young people like me, and make machine learning for everybody, for everyone. So let's dive in together and meet you in Google Colab.
Hey, what's going on everybody? In this video we're going to be modeling the FashionMnist dataset. FashionMnist is a dataset that contains 70,000 images of grayscale images, 28 each, 28 by 28 pixels. So first of all we need to go to Google Colab. So we have to write colab.research.google.com, and then we have to choose new notebook. Now the first thing we need to do is we need to rename this notebook. So we need to rename it, for example, to FashionMnist project, and then we have to connect to the Google's runtime computer, and then wait for it until it connects. Now as you can see, initializing and connected. Now it's connected. Now what we need to do is we need to import the necessary libraries. So first of all, we need to put a comment here, Pytorch computer vision project, and then we need to import the necessary libraries. So one of the libraries that we need to use is called Torch Vision. So computer vision libraries in Pytorch. First of all, Torch Vision. Torch Vision is known as being the base domain library in Pytorch for computer vision tasks. So let's write base domain library for Pytorch computer vision tasks. And then we need to use another library called torchvision.datasets. This datasets library is known for its being the main library for the popular datasets in Pytorch. So get datasets if you want to use popular datasets like Cypher 100, Cypher 10, or like the FashionMnist dataset, all contained in this library. So get datasets and data loading functions. Also, it contains some functions that's known for its abilities to load data. So, and data loading functions for computer vision. Thirdly, we need to use a library called torchvision.models. This library contains, or this package contains, the most popular models in computer vision, like AlexNet and LeNet, and a lot of other popular architectures in computer vision. So get pre-trained computer vision models that you can leverage in your own tasks, for your own tasks. Fourth, there's also a library called, or a package called torchvision.transforms. This library contains a lot of functions that deal with image transformations, image augmentation, and a lot of the tasks to pre-process or process images in computer vision. So functions, it contains functions for manipulating your vision data, for example images, to be suitable for use with an ML model. And then fourthly or fifth, we need to use a library called torch.utils.data.dataset. This is actually a class that is the main class for datasets in Pytorch. So base class, the class that for Pytorch datasets. And then lastly, there is a class called torch.utils.data.dataloader. This class is used to creates a Python iterable over a dataset. So with that being said, these are all the libraries that we're going to use in this project. First of all, we need to import them. So let's put a comment here, import Pytorch. So we need to import Torch, and then from Torch import NN. NN is the main library in Pytorch that contains a lot of pre-created layers for deep learning tasks. For example, NN contains the linear layer, contains the dense layer, contains the convolution 2D layer, contains a lot of other layers that are used in deep learning. Even it contains multi-height attention layers and so on. And then we need to import Torch Vision. Torch Vision, as we said before, it's the main library for computer vision tasks in Pytorch. And then from Torch Vision import datasets. As we said before, datasets is the main library in Torch Vision that contains a lot of popular datasets like Cypher 100, Cypher 10, and a lot of other datasets. Also, for example, ImageNet and so on. And then from Torch Vision import transforms. Transforms, as we said, contains a lot of functions that are used to pre-process images, to flip images, to crop images, and to do a lot of the geometrical operations on images. From Torch Vision.transforms import to tensor. The main class that we're going to focus in Torch Vision.transforms is the class toTensor that's used to convert images to tensors. In order to train a computer vision model, you need to turn images into numbers. You need a way to convert images into some way into numbers, into arrays, into tensors, in order to be able to train the models, the machine learning models. And then import matplotlib. Well, matplotlib is fundamental for visualizing. Always you have to visualize the data. You have to understand data. You have to become one with the data. Every machine learning project or every data science project, the data scientist or machine learning engineer needs to understand the data well, needs to deal with known data. Always you have to become one with the data. So import matplotlib.pyplot as PLT. And then lastly, we need to print the versions of Torch. So torch.version and then __ version. Print Torch Vision.version. Now, if we run this, as we notice here, we have Torch 2.6.0. This is the version of Pytorch currently, of the time of this of recording this video, plus CUDA version is 12.4. And then the version of Torch Vision is 0.21.0 plus CUDA version is 12.4. Okay, with that being said, we need to get a dataset to deal with. Every machine learning project starts with a dataset. Without a dataset, what are we going to model? We need a dataset to deal with, to model it. To be able to build models, you need a dataset. So let's comment this, getting a dataset. Well, to get the FashionMnist dataset, we need to use the library datasets. So first of all, the first step we need to do is we need to create a variable called train data equals datasets.fashionMnist. This is a class inside this library datasets. If you look up now Torch Vision and enter the first website here, we notice here the Pytorch documentation. As you can see here, Torch Vision, this library is part of the Pytorch project. The Pytorch is an open source machine learning framework. So Torch Vision is a part of the Pytorch project, and it is commonly used for computer vision tasks, and it contains a lot of sub-packages like transforming and augmenting images, TV tensors, models and pre-trained weights, datasets. Now, the library that we need to use to fetch the data of the FashionMnist is called datasets. If we click on this datasets, you notice here Torch Vision provides many built-in datasets in the Torch Vision.datasets module, as well as utility classes for building your own datasets. Wow, that's nice. So if you go down, you'll notice a lot of pre-loaded datasets in Torch Vision.datasets. For example, CIFAR 10 and CIFAR 100, and also, for example, eMnist and Eurostat and fake data. Wow, FashionMnist also exists here. So FashionMnist, this is the dataset that we're going to model in this video. This class takes from me several parameters. The first parameter being root. Root is where do you want to download this data to. So if you pass in here, for example, root as data. So root represents where to download data to. And then takes from me train. Whether this dataset is being used for training or for testing, for training the model or for validating, for evaluating. So train, we're going to set it to true. Yes, this is training dataset. This is the training set. And then we have to pass in download as true. Download, do you want to download this dataset? Yes, we do. We definitely want to download this dataset. And then transform. This parameter is an important parameter because it specifies the operations, the mathematical operations that we want to apply on these images, For this context, or in this specific project, we're going to use two tensor class. This class is used to convert images into tensors. So we need the images in the tensor form. We need images in the tensor form to be able to train the model. And then target transform. What transformations do we want to apply on the targets? Currently, none. None of the operations we want to apply on the targets. This is for the trained data. Now we need to do the same thing, the same process of the test data. So test data equals datasets.fashionMnist class, and then pass the following. The first parameter, root, so root to pass data, and then train equals false. This time we want to get the test dataset, not the train dataset. And then we need to pass download as true, and then transform the same thing to tensor. We need to convert images to tensors, and then lastly target transform as none. Now if we try to run this cell, okay, there's a comma here. Yeah, we need to put a comma here. Classic error. Now, as you notice, we are getting the dataset. Now it's fetching, it's grabbing the dataset, and yeah, target transform, target, there's a misspelling here, target transform. Now if you run again, the data is being downloaded here. If you open this files section in Colab, you'll notice there's a folder, a new folder called data, as we specified here. Root is data, and then this data folder contains a folder, a subfolder, or a folder inside this called FashionMnist. This folder contains raw data. So we have raw images, okay, as you can see here. Now we have downloaded the data correctly. We have downloaded the data successfully. The next step is to become one of the data. So let's inspect some of the parameters, some of the attributes, some of the properties of the data. So what is the length of trained data? How many images do we have in the training set? Whoa, we have 60,000 images in the training set. What about the testing set? How many images in the test set? We have 10,000 images in the testing set. So we're going to try to build a model to find patterns in 60,000 images, and then we're going to evaluate those patterns, to evaluate those parameters, those learned parameters on these 10,000 images. Now let's move on to the next step. After we have seen how many images in each set, let's try to get the first training sample. So see the first training sample. To get the first training sample, we need to create two variables, the first called image and the second called label. Why? You might have the question, why do I have to create two variables like this? Because each sample in the set is containing two significant elements, an image and its associated label. Each image is associated to a label. So each image has a label. So we need to create two variables, the first called image, the second called label, to get the first sample correctly. And then let's access the trained data variable and then index it on the 0th index. Now if we see this image variable, ooh, a whole bunch of numbers. So this is an image, but in the form of a tensor. So we have represented the images as tensors, which is a significant process in building computer vision models. Always you have to turn your data into some form of numbers, into some form of numerical format, numerical encoding, to be able to build a model. So as you can see here, this is a tensor full of numbers, a massive tensor of numbers. And then what about the label? What is the label of this image? Whoa, 9. So the label of this image is 9. I wonder what 9 means. What does the label 9 means? Well, to know that, there's a significant property in the trained data dataset. Now, if you visualize the trained data, we're going to notice it's a dataset. It's a Pytorch dataset called FashionMnist. Number of data points 60,000 images. Root location data. Split train. Standard transform to tensor. But if you access a property in this object contains a property, an attribute called class and classes. This property retains a list full of the label names, the names of the labels. So t-shirt, top, trouser, pullover, dress, coat, sandal, shirt, sneaker, bag, ankle boot. So 9 relates to ankle boot. Okay? So we need to store this list in a variable called class underscore names. Now we are able to pass this label variable to the class names variable. So pass label. Now we have got ankle boot. So we have gotten the corresponding label, the corresponding target of this image. So this image is relating to the label ankle boot. This image represents an ankle boot. Now, if we want to visualize this image, always visualize, visualize, visualize. If you want to visualize it, we need to know the shape of this tensor. So image.shape, we will get, whoa, that's interesting, 1, 28, 28. So what does 1 mean? 1 is the number of color channels. The number of color channels. 28, this represents the height of the image, and 28, this represents the width of the image. So we need to get rid of this color channel to be able to visualize it with Matplotlib. So to get rid of this one color channel, we need to squeeze the image. So image.squeeze, and then if you display the shape of this image, whoa, we have gotten 28 by 28. We have gotten rid of the color channel here. Now all we need to do is pass this squeezed image to the plt.imshow function. Now, whoa, that's an image of ankle boot. So that's how easy Matplotlib makes it to visualize an image. Now we need to turn this image from the colored mode into some mode that represents the number of color channels for this image. We have discussed that FashionMnist contains 28 by 28 grayscale images. So if you want to show this image in the grayscale form, maybe we'll put it in a new cell. We need to pass plt.imshow and then pass the image.squeeze and then specify the scene map, the color map, as gray to specify that this image is of grayscale image, like that. So FashionMnist is a dataset that contains 70,000 images in total, 60,000 for training, 10,000 for testing. Each image is of height 28, of width 28, and being a grayscale image. Now if we specify the title of this image, plt.title, and then pass the label as it is, we will get the number 9. But if we index on the class names variable, we will get the name of this image, or the label. As you can see here, ankle boot. So we have gotten the ankle boot title for this image. Now we have visualized the first sample. We may do the same thing by visualizing the other samples, but I'm a big fan of randomness. Randomness is an important topic in machine learning. So let's create a mechanism that randomly show 16 images at a time. So that's a wonderful idea. What about we do it now? But before we do it, I want to show you some properties about this train data object. So there's also another property called class to IDX. So train data and then dot class dot underscore to IDX. And then if you show this variable class to IDX, it's just a dictionary that contains the keys as the names of the labels, and the values are numbers associated to these labels. As you can see, t-shirt, the label of t-shirt is 0, the label of trouser is 1, the label of pullover is 2. So these names are for us as humans. We humans like to read things in textual format, but models, computers, machines like to deal with numbers, with some numerical format, with some numerical encoding. So these are for machines, and these for us as humans. So this is a dictionary, and then there's also another property called targets. Train data dot targets. This property retains a big long tensor of all the targets of the train data. If you show the first 100 samples, these are the labels for the 100 samples of images. So the first 100 images, these are the labels that are associated to them. So 9 ankle boot, 0 t-shirt top, 0 t-shirt top, 3 whatever dress, 2 so on, so on, so on, until we finish the number of data samples in the train data. So with that being said, now we need to move on to how we can visualize 16 images in one hit. So first of all, let's put a comment, plot more images, and then torch.manual seed. We need to set the manual seed. Well, is it necessary? No, it's not mandatory to set the seed, but it's always a best practice to fix the seed, to somehow get the same numbers, to get a reproducible experiments, reproducibility, an important topic in machine learning. And then figure or plt dot figure, and then pass fig size. The size of the figure is 9,9, so we have 9 height, 9 width, the size of the figure, and then rows, comma, columns. How many rows do you want? 4. How many columns do I want? 4. And then we're going to create a for loop. So for a simple for loop for I in range of start from 1, and then rows times columns. So rows times columns is 16 plus 1, and then we need to, every time, every iteration, we need to generate a random IDX. So random index equals torch.randint start from 0 to the length of trained data. So again, what is the length of trained data? The length of trained data is 60,000. So we're going to generate a random integer between the range of 0 until 60,000. So if we go like that, torch.randint, and then start from 0, and then until the length of trained data. Now, if you don't specify a size, we're going to get an error, because this is an important and required parameter. Now, every time we run this cell, we get a random index. We get a random index, a random integer between 0 and 60,000 to get random images. As you notice, these are randomized images, randomized numbers, randomized integers. And if you want to get this number specifically without the tensor being wrapping this number, dot item function does that for us. As you can notice, we are getting random integers to fetch random images. So we need to incorporate this inside the for loop, or to embed this inside the for loop. Size equals 1, and then dot item. Now, if you want to fetch these images from the trained dataset, image comma label equals trained data object, and then access the random IDX, whatever it was, then plt or fig dot add subplot. We're going to add a subplot each time, each iteration we're going to add a subplot. So rows comma columns comma I, so the ith position in the figure. plt.imshow, we're going to show the image comma cmap as gray, as we've discussed before. plt.title, the title of the image is the class names, and then index on the label. Then plt.access false. Now if you try to run this cell, whoa, an error. So let's read the error. Invalid shape. As we said before, this image is being color channels, height, width. So as you notice here, we have color channels, height, width. In order to plot grayscale images, in order to show grayscale images in Matplotlib, we need to get rid of this color channel. And how we do that? By using the squeeze function. So a classical error, and then run. Hooray! We've got 16 images being showed up as a figure. So each time we run this cell, we're going to get the same images. Why? As you notice here, this ankle boot not being changed when we run the cell. Why? Because we have set the manual seed. If we comment the manual seed, we're going to get different images each time. Yeah, run. We have dress, sneaker, t-shirt, top, trouser, and so on, so on. So if we notice that here we have some confusing labels or some confusing categories. For example, coat and pullover have similar shapes. So we may then plot a confusion matrix that shows some confusion. The model is being confused between these labels because they have similar shapes, they have similar patterns. And then if you run more, you're gonna notice bag. This is a bag. This is a pullover, a trouser. Here we have trouser, sandal, ankle boot, shirt, sneaker, and so on. So this is a mechanism of showing 16 images each time differently. As you notice, we have pullover, sneaker, dress, so on, so on. Now we have visualized a figure of images. We have become one with the data. The next thing, now this step is very important. Now we have images, we do have images, but is it reasonable that we're going to build a model that take a look, or that can take a look at all these 60,000 images at one time? That's crazy, because if you build a model, we can reassign the seed as 42, and then we can get the same images as before. Okay, so as we said before, if we try to build a model that can take a look at 60,000 images at one time, that would be incredible. But in modern computer vision tasks, 60,000 images is not that big of a dataset, because modern image datasets contains 14 million images. For example, ImageNet. If we go to ImageNet, this is the official website of the ImageNet. ImageNet contains 14 million images of 1,000 different categories or 1,000 different classes. But ours, in this case, we just have 60,000 images. Even if it was 60,000, the model may not be able to look at these 60,000 images in one hit. So we need to convert these images into batches. We need to turn these images into batches or mini batches in order to train the model effectively and efficiently. So, the next step, or 3, prepare a data loader. So what is the purpose of a data loader? Why do we have to use a data loader? Well, right now, currently, our data is in the form of Pytorch datasets. Our data is in the form of Pytorch datasets. Okay, so what we need to do is we need specifically, we want to turn, in other words, convert our data into batches or mini batches. And how we do that? Pytorch offers a class called data loader that is used to convert data into batches or to split data into batches. So why would we do this? Why would we do this? For 2 reasons. The first one being it is more computationally efficient. It's more computationally efficient because if we try to train the model on 60,000 images in one batch, that would take a lot of time. That would take a long time to fit the model. So we need a way to turn these images into batches, into groups, into subgroups, into subcategories, to train the model efficiently and effectively. So, as in your hardware, your computing hardware, so our CPU, this is our computing hardware, RAM and disk. RAM 1.89 gigabytes and disk 37.09 gigabytes. So right now, your computing hardware may not be able to look at mean, in other words, to process, in other words, to store in memory. Our model may not be able to store the data, all 60,000 images, to store them in memory in one time or in one hit. So our model may not be able to look at 60,000 images in one hit. So we break or split, or we need a way to break our dataset down to 32 images at a time. So our model can store these images in the memory. So at a time, meaning batch size of 32. And then the second reason why would we do this is it gives our neural network more chances to update its gradients, in other words, its weights per epoch. Well, that might sound complex in the first time, but it's more efficiently. As Jan LeCun said, if you search Jan LeCun batch size, Jan LeCun has a great tweet about batch size. If you read it here together, training with large mini batches is bad for your health. More importantly, it's bad for your test error. Friends don't let friends use mini batches larger than 32. So Jan LeCun is a popular pioneer in machine learning or deep learning, who has a great articles and great viewpoints in deep learning world. So he said now, friends don't let friends use mini batches larger than 32. So this is kind of a saying in deep learning, a popular saying, that always you have to set your batch size to 32. Okay, now if you go back to here, and as we said before, it gives our neural network more chances to update its gradients. So rather than our neural network just look at 60,000 images in one hit and update the gradients just one time, no, we will have more chances to update the weights many times in one epoch. So rather than updating the weights just one time per epoch, we want to update the weights many times in one epoch. So that is the premise behind dividing our data into batches. So now, if we show the train data is just a data set called FashionMnist. The number of data points, 60,000 images, route location data, split train, standard transform to tensor. This is a dataset that is not yet batched. Now, to turn it into batches, we need to import a class from Pytorch. So from torch.utils.utils.data import the class data loader. So this is a class called data loader. This class is the heart of loading datasets, loading large datasets into models. If you search here torch utils.data loader, you will get this Pytorch documentation. Torch utils.data. At the heart of Pytorch data loading utility is the torch.utils.data loader class. It represents a Python iterable over a dataset. With support for map style, so it maps between images and labels, and iterable style, so it is being in the iterable style format. So batched, a batch of 52, then a batch of 52. So it's being map style and iterable style datasets, customizing data loading order. We can customize the order, so we can shuffle the data. We can get the data in the same order, or we can also shuffle the data to get it mixed up. Automatic batching, single and multi-process data loading, automatic memory pinning. So these are all the features of using this data loader class. So why don't we use it right now? First of all, we need to set the hyperparameter. So set up the batch size hyperparameter. So we as machine learning engineers, we as data scientists, there are some settings, some configurations in the models that we need to set ourselves. These settings, these configurations are called hyperparameters. Anything that is able to be changed by a machine learning engineer, by a DL engineer, this is called a hyperparameter. While parameters are those values within the model that the model tries to optimize. The model tries to adjust and modify in order to best or to better represent the data. So here we can set the batch size. We have to make it capitalized because it's a hyperparameter. It's a convention in the world of machine learning. You're going to notice that hyperparameters are being written in capital letters. Batch size equals 32. Now this number could be changed, could be 64, could be 128, could be 256. Any number you can change and try. So this is a parameter that is experimental. Always as a machine engineer you have to experiment. So you may experiment with 32, and then the next experiment you try a different number. Try for example 64 at the batch size, and then change it to 128, and then for example 256, so on so on. So it is a hyperparameter that you can change. So let's first start with 32 as Yan LeCun said, and then turn datasets into batches, into iterables, or in other words into batches. So train data loader equals, this is a variable, this is a new variable called train data loader, equals this class data loader. This class takes from me three main parameters. It expects from me a dataset to convert it into batches. It expects batch size, so the size of the batch, and then it expects whether we want to shuffle or not. And it also expects a lot of other parameters, but these parameters are pretty good defaults. So first of all, we need to pass in here train data, and then specify the batch size as this variable, batch size 32, and then we need to specify shuffle equals true. Yes, we want to shuffle the data. Shuffle equals true. When you shuffle the data, you will get better reliability, you will get better reproducibility, and get better validity of the model, because when you get the data in the same order, the model will be biased. So to get rid of the bias, to remove bias, to delete bias, we need to shuffle the data in order to get a better reliability, validity, and reproducibility of the model results. Now we need to do the same for the test data loader. Equals data loader class, and then pass test data. This is used on the test data, or this data loader is being applied on the test data, while this data loader is being applied on the train data. And then we need to pass in the batch size, the same batch size actually, 32, and then shuffle. Well, in here there is an important distinction between training set and testing set. The testing set doesn't need to be shuffled, so you don't have to shuffle the test data. You don't need to shuffle the test data. So we may set the shuffle as false. Why? Because the model will not see the test data in the training phase. In the training phase, we will show the model just the training samples, the training examples, but the testing data is used just for evaluation, for testing the model. Now, what about we show these loaders, train data loader and test data loader? Beautiful. Now we have gotten two data loaders ready to be trained. So torch.utils.data.dataloader stored at this location in the memory, and then torch.utils.data.dataloader at this location. So these are two data loaders being set up for training the model. Now, if you want to check how many batches do we have, how many batches, we can print some pretty good statements here. So let's check out, always inspect your data. So let's check out what we have created. So print data loaders are train data loader, comma test data loader, the same that we have printed above, and then print f string length of train data loader. How many batches do we have in the training set? So length, the len function, and then pass train data loader, batches of batch size, and then dot dot dot, and then print f string length of test data loader, and the length, we have to print the length of test data loader batches of batch size. Now these are just simple print statements that would show how many batches do we have in each set. So if you run this, you'll notice data loaders, as we said before, it's torch.utils.data.dataloader.dataloader. This is the data loader being applied on the training set, train data loader, and this is the data loader being applied on the test set, as we said before in here. But the new thing in here, the length of train data loader is 1875 batches of 32. In other words, we have 1875 batches of 52, which is amazing. So we've got 1875 batches going through the model. And after each batch, the model will adjust the weights, will modify the weights based on what the model has seen. And also the length of test data loader is 313 batches of 32. So we have 1875 batches. Each batch of these batches contains 32 images, 32 samples, so the total is 60,000 images. And if we do the same thing here for the testing, we have 313 batches. Each batch contains 32 samples, so we have in total 10,000 images. Now you're going to notice that we have 10,016, and you might have the question, whoa, from where did these 16 images have come? Well, that's a very valid question. Why? Because this data loader class rounds up the number of samples. The data loader class rounds it up. When data loader creates batches, it will round it up. How? Now, if we want to get this specifically, how many batches do we have? If we divide 10,000 by 32, we will get 312. But data loader class rounds it up to 313. So the last batch contains some duplicated images. So the last batch contains some duplicated images in order to fit the number of batch size and in order to fit the number of training samples or the number of testing samples. So this is the number of samples in the testing set. 16 is just a duplication. If you want to drop the last batch, that's available through this property. If you go test data loader dot drop last, this is a property that is used to drop the last epoch if you want. But in this case, no, we don't want to drop the last epoch, even if it contains some duplicated images. That's perfectly fine. Now let's go to the next step. Now we have turned our images into batches. We have turned our dataset into batches, and we can verify that further by printing or by using the shape property. If you can go train data loader and get the first, or we can wrap it into iter. We can convert it into iterable, and then convert it into next. We will get a list containing tenses in this shape and then some labels. Why? Now you might have the question, why do we have just these tenses and just these labels? Well, this is a batch. This is now a batch. If we count this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, and 32. So we have 32 labels. We have 32 images in this list. We may have a more in-depth inspection by storing this into some variables. So we have batch images. So we have a variable that contains these tenses These instances are nothing but images, comma, batch labels. Now, if we do this thing, I'm going to show you something in here, something very in-depth. Batch images dot shape. So what is the shape? I want you to have a think for a moment before I run the cell. What is the shape of this batch? Well, it's 32 by 1 by 28 by 28. So we have 32 images. 32 images. Each image has one color channel, and also each image has 28 height and 28 width. So this is a batch. This is a batch of the trained data loader. We have converted it into an iterable, and then next, for meaning give me the next batch, and then we have stored the images in this variable and stored the labels in this variable. Now the same thing if you try to get the shape of the labels. I want you to have a think for a moment. What is the shape? What is the shape of the labels? Well, it's these labels, and if you try to get the shape of it, we will get 32. So we have 32 labels. Now you might have the question, why these images have color channel, height, width? Well, because these are images, while these are labels. These are just numbers, so they don't have dimensionality. They don't have width, height, and so on. So these are just labels being in a tensor. So 32 labels. While the images are 32 images, each has one color channel, and it's 28 by 28 height and width. If we try to visualize an image from this batch, we can do that by doing the following. Visualize one sample from the batch, just to verify that we have done everything in a good way. The first thing, we need to turn on the torch.manual seed to get the same image, 42, and then we have to generate a random index. Random IDX equals torch.randInteger, start from 0 until the length of batch images. So what is the length of batch images? How many images are in this batch? How many images are in this batch? We have 32 images. So the length of one batch is 32. So we want to generate a random integer between 0 and the length of batch images, which is 32. And then the size is 1. Dot item, we will get, each time we will get a random integer in the range of 0 until 32. Okay, and we will take that random IDX and visualize it with matplotlib. So size equals 1 dot item function. And then the next step is image, comma label. Now we want to get the image from where? From the batch images variable. So batch images, and then access this random IDX, and also the label, the same thing. We have to access the batch labels and pass the random IDX to get the same index. plt.imshow, we want to show this image. We want to display this image, and then pass image.squeeze. So why do we have to squeeze the image? Because it has one color channel, and matplotlib expects this color channel to be removed, to be deleted. And then the CMap, the color map as gray, because they are grayscale images. And then plt.title as labels or batch or class names. If you want to show the name of the class, and then pass the label of this label, pass the label and index on the class names list. Class names is nothing but a list that contains the names of the classes: t-shirt, top, trouser, pullover, and so on. And then we wanna, if you wanna get rid of the axis, I wanna show you this. Now this image contains axes, So if you want to get rid of this axis, plt.axis, and then pass false, or we may have to pass off this time. Both ways work. Now we don't have axis anymore, so we might have passed false, also works, or off, both ways work in the same way. So now we have a sneaker. If we uncomment this torch manual seed, we will get, each time we run this cell, we will get a different image. We will get a different image. So now we have ankle boot, and then if you try again, this is a shirt, this is a bag, this is a trouser. So the idea here, we want to train a model that learns the edges, of these shapes. Okay, we want it to learn the edges, the corners, the colors of these objects, and then we want it to learn the shapes of these objects. So the shapes of these images, for example, the coat has this shape, this specific shape here, this specific edge here. So the model will try to learn the patterns, the edges, the corners, the colors, the shapes, starting from the simple patterns towards the more complex patterns. For example, it will try to learn that this is a square-like shaped, this is a triangle shaped, a triangle-like shaped, and so on, so on. So the model will try to learn these patterns, learn these figures, learn these properties through using backpropagation and gradient descent as the optimization algorithms. Now we have, speaking of backpropagation, speaking of gradient descent, why don't we try to build a model? So that's an exciting step. 3 or 4, model 0. We will build a baseline model. We're going to build a baseline model. So build a baseline model. So how to create a model in Pytorch? To create a model in Pytorch, firstly, we need to create a class, and then we're going to name this class. So you can name it whatever you want, but there is one condition, that you have to use Pascal case as the naming convention for classes, because OOP, Object Oriented Programming, uses Pascal case as the naming standard convention. So I'm gonna name it Fashion. Notice the F is capitalized. FashionMnist model version 0. So this is the first model that I'm going to build to model this dataset. And then this model will inherit from, or will subclass, in other words, will subclass nn.module. nn.module, if you search here, nn.module is the base class for all neural network modules. So the base class for all neural network modules is module here. And notice in here, your models should also subclass this class. Okay, so that is an insightful notification in here. So thank you, Pytorch. And then, so it said here, your models should also subclass this class. And here we have subclassed the module class for our FashionMnist model version 0. Now this class, this is a class. We need to create an initializer, or the constructor inside this class. So def __ init. So the init method. The init method takes from me the self keyword. This is an important keyword. And then takes from me input shape. The input shape. So how many inputs to this neural net. And then we're going to specify a type hint in here as int. So input shape should be of type integer. And then hidden units, the number of hidden units in the network as integer. Output shape as integer. So these are the parameters that we need to pass every time we subclass or we need to instantiate a new object from this class, FashionMnist model version 0 class. Well, in order to create this class now, we need to call the super method. So the super function. Super is the parent of this class, which is module, and then call .init. Now, the next step we need to do, we need to construct the model architecture. So what is the model architecture? Because this is the first model that we're going to build, we're going to keep it simple. So we're going to have to specify an attribute called self.layerStack. So the stack of layers, we need to stack those layers sequentially. So we're going to use nn.sequential, the sequential class, and then pass nn.flatten. Now you might wonder, why do we need the flatten here? Well, we need a flatten layer because the images are of 2 dimensions. If we try to get some image in here, so image, and then access the shape property, you'll notice that we have emitting the canal channels, we have height and width. So we have 2 dimensions. We have a matrix. We have a tensor of 2 dimensions. And in order to use this matrix through the linear layer in Pytorch, it requires these inputs to be flattened, to be squeezed, to be in one long tensor. Now I'm going to show you the flatten here. So I'm going to specify a variable called, for example, my flatten layer equals nn.flatten layer. And then if we just show this flatten layer, it's just a flatten layer. It's just a simple flatten layer, nothing fancy in here. The important thing in here, I have an image in this shape. Notice I have vectors, I have lists, I have dimensions, height, width, a lot of dimensionality going on here. So in order to get rid of this dimensionality, in order to collapse this tensor into one long vector, we need to pass it to the flatten layer. So my flatten layer, and then pass this image. We will get, whoa. Now notice that we have just one tensor. We just have one tensor of all these pixels, of all these numbers. If we try to get the shape of it, dot shape, it will be, 784. So from where did this number come from? Well, if we multiply 28 by 28, we will get 784 pixel. So flatten simply takes a 2-dimensional tensor, takes a 2-dimensional matrix, and then collapse it or flattens it into one long vector of the same shape but multiplied. The height multiplied by the width. Okay? So now, if you want to visualize this image, we have image, this tensor, dot, and then access the attribute squeeze, or the function, and then pass it, or the function squeeze, and then pass it to pl2.imshow. Notice we will get this image, ankle boot. But we don't want the image to be of height and width. We need to collapse this tensor. We need to get rid of the dimensionality and make it just one long vector that contains the height and width as one vector, as one long dimension. So if you search in here flatten layer in NeoTorx, we will get plenty of resources here, a plethora of resources. For example, if we read in here, what does a flatten layer do? Reducing model complexity. So firstly, it reduces the complexity of the data. The flatten layer reduces the dimensionality of the data, which can help reduce the number of parameters in the subsequent fully connected layers. This is important to manage model complexity and to avoid overfitting, especially in deep networks. And it also, if you search for flatten in NumPy, you will notice that flatten retain a copy of the array collapsed into one dimension. So it retains a copy of the array collapsed or flattened into one dimension. The same thing goes into here. If we try to flatten this image using my flatten layer, and then pass the image in here, what do you think? Will it be able to visualize it or no? Let's see. 1, 2, 3. No, it's not able because it's one long vector. as you can notice, this is a one long vector of all the numbers. So we can't visualize the image anymore, because images, when you want to visualize images, it needs to be of height, the dimension, and width dimension. When you get rid of this dimensionality and make it just one long vector by using the flatten layer, you will get just one vector, not an image. But this vector, the model, is able to figure out the patterns, to discover the patterns, to discover the parameters within these underlying huge datasets. One thing is if you want to visualize the shapes of, for example, image before flattening is image.shape, and then if we try to print image after flattening is image, or my flatten layer, and then pass image.shape. Now notice here, image before flattening, torch.size 12828. So this is the image shape before flattening. But after flattening, we have 784. So we have collapsed the height and width into just one dimension. Okay, that's the whole premise behind flatten. Now after flatten, we will use just two linear layers. Just two linear layers. If you search in here, linear Pytorch, linear layer, applies an affine linear transformation to the incoming data. So y equals x multiplied by the weights plus the bias. So we have this equation. The y is the output of the model, x is the input to the model, a is the weights matrix transposed, plus b the bias. So this linear layer applies an affine linear transformation to the incoming data, and it takes from me two important parameters. It takes from me in features and it takes from me out features. So let's pass in here nn.linear. We're going to use a linear layer dot linear. This linear layer takes from me an in features property equals. Now I want you to have a think, what is the number of neurons in the first layer? If we have 784 inputs to the model, what is the appropriate number of neurons to this layer? Well, will be 784, because we have 784 data inputs going through the network. We need to have 784 neurons or nodes or artificial nodes for this network to be able to receive the data appropriately. And then we need to pass in out features. How many out features do we want to output from this layer? So each linear layer takes from me some input shape and some output shape. One of the main and significant aspects in machine learning and deep learning are the shape aspects. So always we have to align the shapes up. We have to align the shapes. We have to align the input shape with the output shape. So if you have this number of inputs to this network, we may define the out features as 10 out neurons. So this linear layer receives 784 neurons or inputs, and then outputs 10 neurons or 10 outputs. And then we're gonna put another linear layer, nn.linear. This is just a linear layer, a linear or dense layer in TensorFlow. In TensorFlow, they name it dense. And then it takes from me in features. How many in features? Here is an important tidbit. Now, if you said that the previous layer outputs 10 features, what is the appropriate in features for this layer? Also will be 10 features, because the previous layer outputs or outcomes 10 features. This linear layer should receive also 10 features, should receive 10 inputs. And then, what is the out features? Well, this will be a little bit tricky because it depends on how many classes do we have in this set, do we have in this training set. If you go to class names, now the whole idea here is we want to build a neural network that receives images and then outputs the label or the name of the image. So how many classes do we have in here? How many categories do we have? Well, if you pass it to the length, you don't have to count because we are programmers. We like to automate things. The length is 10. So we need to specify in the output layer, we need to specify how many output features as the length of class names, which is also valid if you use 10 in here. Both ways will work. But if you want it to be dynamically, we may use the length of class names, which is more dynamically and more able to be adaptive. If you add more labels in the future, it will contain whatever the number of features or the number of classes it contains. So out features equals length of class names, because we have 10 classes. So 1 neuron per class. Why? Because this model will output logits, will output prediction probabilities. So we need a probability for each class. So the model will assign a probability to each class. So when a model sees an image, okay, this is an image, I think it's 20% shirt, I think it's 30% sneaker, I think it's however many percents this class. So we need a probability for each class. And in order to get this number of probabilities for each class, you need also to define the output layer as the number of classes. So in regression problems, the output layer contains just one neuron. If you are doing regression problem, or if you are building a regression model, the output layer will contain just one neuron. Whereas in binary classification, the output layer contains also one neuron, because it classifies whether it is one thing or another. So it will output just one probability. While in multi-class classification, as in this case, we have 10 classes, so we need to define the output layer to contain 10 neurons. If you search up what is a network in here and go to images, this is the architecture of a simple network. And if you search for network for FashionMnist, specifically for FashionMnist, you will get, notice in here. Now this network will receive a 28 by 28 pixels image. So MNIST fashion dataset 28 by 28 pixels images. And then we have 784 neurons in the input layer. Why? Because 28 times 28, we will get 784 input neurons. And these input neurons will pass these data through this hidden layer. So this hidden layer in this case contains 128 neurons. In our case, we have made it just simple, 10 neurons. But in this image, they have specified it to be 128 neurons. And then, how many neurons are in the output layer? We have 10 output neurons in the output layer. We have a t-shirt, a neuron for t-shirt, a neuron for trouser, a node for pullover. We have a node for dress. We have a unit for coat, and so on, so on. So each class needs a neuron, needs a node, okay? This is an important aspect in machine learning, how to align up the input shapes with the output shapes. Now, we have specified the architecture of the class or of the model. We need to specify the forward propagation. So def forward propagation, and then pass self comma x. Return self dot layer stack. We need to call this layer stack attribute, and then pass x. We need to pass the x, the data. X is just the input data. So x is input data. So we need to pass this input data through the model, through the layers, and then return it in the forward method. So with that being said, we have created our model. Now we need to instantiate an object from this model. So to instantiate an object, we need to name the object. So we're going to name it model 0, for example, or you could name it anything. You can name it model or model FashionMnist, anything you want. Doesn't really matter. So we need to name it model equals the name of the class, FashionMnist model version 0, and then specify the parameters that we have set before. Input shape. So how many neurons do we have? 784. And then hidden units. How many hidden units do we have? We have 10 hidden units. And then output shape as 10 equals 10. Okay. Well, you could make it the length of class names. Length of class names. Now, we haven't really used these numbers in the network explicitly. So we need now to replace these with some dynamic parameters. Input shape, hidden units, and then here also hidden units. I just used those for explanation purposes, and then output shape. And these will be replaced with the inputs that I have passed in here, okay? And then if you show the model, what is this model? Wow, it's a FashionMnist model version 0. It's in fact a sequential model that contains one flattened layer, two linear layers. The first linear layer acts as the input layer, receives 784 inputs, and the out features of this layer are 10. And then the next layer receives also 10, aligning up with the out features of the previous layer, and then it outputs 10 probabilities, one probability for each class. Now, if you want to look up what are the parameters, what are the state dict of this model, wow, look at those, how many parameters we have. We have a lot of weights, biases, parameters that we need to optimize. We need to adjust, not us, but the backpropagation and gradient descent algorithm. So layer stack 1 dot weight, these are the weights associated with the first layer, and these are the biases associated with the first layer, and these are the weights associated with the next layer, and these are lastly the biases associated with the next layer. Now these weights and these biases are initialized randomly, so they all random. They just horrible, terrible weights and biases. They are not perfect. So now the model names the shirt as sneaker, names the sneaker as ankle boot, and mix everything up. So we need now to train the model to optimize the parameters, to optimize these parameters, to fine-tune these weights and biases in order to better represent the data, in order the model that is able to name the images as their real names. So now if you try to pass a test or dummy forward propagation, if you try to do a dummy forward propagation here, like that, I'm gonna choose an image. This is an image, contains a lot of pixels dot shape, as you can notice here, 1, 28, 28. Now we need to pass this image through the model. How to pass this image through the model? Well, that's easy. All you need to do is you need to unsqueeze the image. Why do we have to unsqueeze it? Because we need to add the batch dimensionality. Now we have just scale channels, height, width. We don't have batch dimension. So unsqueeze is the inverse operation of squeeze. Squeeze squashes the data up, while unsqueeze adds more dimensions. So unsqueeze, and then we're going to have to specify dimension as 0. Now we will get an additional shape. Whoa, 1, 1, 28, 28. So we have the batch size here in this specific case in this specific dummy demo for propagation 1, comma, the channel 1, and height 28, width 28. So we need to pass this image, we need to pass it. So here, dummy x, and then pass this image through the model, and then pass dummy x. Why do we have to do this? Why are we doing this operation? Because we want to verify that we will get 10 probabilities, that we don't have issues with the input shape, with the output shape, everything is going well, and then if you saw that everything is well, we can train the model. So now, hooray, we have 10 probabilities for each class. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 probabilities for this image. So now what we have done now is we have passed an image through the model, even if it contains random weights, crazy biases, it was able to produce 10 probabilities. Each probability, this is for t-shirt or top, this is for trouser, this is for pullover, dress, and so on. So these are logits raw outputs from the model. We need to convert them into softmax to convert these logits into prediction probabilities, and then we need to convert it into using the argmax, convert these probabilities into labels. Now we have verified that our model is good, our shapes is really good. We can train the model. So let's move on to the next step. 3.1 set up loss and optimizer and evaluation, or set up loss, comma, optimizer and evaluation metrics. Well, first of all, we need to ask some questions. This is a multi-class classification problem. What is the appropriate loss function to use? Is it binary cross entropy, BCE, or is it cross entropy? So if we need to set up the loss function, loss underscore fn, this is a variable, this is a brand new variable, equals nn neural networks dot. Now, as I asked before, do we have to use BCE, binary cross entropy, or do we have a multi-class classification problem and we need to use cross entropy? Well, in this case, we have a multi-class classification problem. We classify objects into whether it was one thing or one thing or one thing, or so multi-class classification. So we need to use the cross entropy loss as our loss function. And if you search that up, cross entropy loss in Pytorch, Pytorch library, you'll notice that we have cross entropy loss in here. This criterion computes the cross entropy loss between input logits and target. Very nice. It's useful when training a classification problem with C classes. See here, as I said before, it's useful when training a classification problem with C classes, meaning with N classes, with 10 classes, with 4 classes, with whatever number larger than 2 classes. If provided, the optional argument way should be a 1D tensor assigning weight to each of the classes. This is particularly useful when you have an unbalanced training set. So if you have an imbalanced training set, meaning we have, for example, 50,000 samples all being as ankle boots, and the rest of the classes are distributed over 10,000 samples, you need to specify some weights. But in our case, we have 10,000 image or sample for each class. We have 10,000 images for sneaker, we have 10,000 images for ankle boot, we have 10,000 images for dress, and so on and so on. So our data set is balanced. Okay, let's go back. And then what about the optimizer? What optimizer should we use? Well, there are 2 options. In fact, if you search in here, torch.optim. The best optimizers for this simple project are, you can use, for example, Adam optimizer. That's one option. You can use also SGD. That depends on you. But in this case, I'm going to try Adam. Adam is a very good optimization algorithm. So torch.optim.adam optimizer. Now notice here, the optimizers in Pytorch takes two parameters. The first parameter, or the first argument, is params. Params are the parameters of the model. So we need to specify the parameters as following: model.parameters. So what are the parameters of the model? Model.parameters, and then we will get a generator. If we turn this into an iter, we will get an iterator, and then get the next, we will get a whole bunch of parameters, of weights, of biases. So we will pass these parameters to the optimizer Adam, and Adam will take care of them, will fine-tune them, will adjust them, will modify them to better represent the data. And then the learning rate. Learning rate is a very important hyperparameter. As we said before, we have batch size. Batch size is an important hyperparameter, and we also have learning rate. Learning rate defines the amount of updating. How much do we want to update the weights? Now you have to keep in mind, the higher the learning rate, the more aggressive the model will update the weights, and the lower the learning rate, the slower the model will take to converge. So it's kind of a balance. As Jeffrey Hinton says, it's kind of a balance between choosing the right and optimal learning rate. So learning rate in here equals, for example, 0.01. For example, I'm going to specify the learning rate as 0.01. It's an experimental hyperparameter. You can change it to whatever you want. Now we have set up the optimizer, the loss function. We need to create a function that acts as our evaluation metric. So define evaluation metric, but I'm going to name it accuracy. We're going to use accuracy. Why are we going to use accuracy? This is an important question. Well, if you have a balanced dataset, it's useful to use accuracy, or it's recommended to use accuracy. While if you have an imbalanced set, say for example you have 20,000 images for one sample and then just 100 samples for one class, well, you need to use precision, recall, F1 score. But because in this case we have a balanced set, we're going to use accuracy. So this function will take from me two important parameters, the first being yTrue, the second being yPred. Well, now we need to create, all we need to do is we need to create a variable called accuracy, for example, or correct, whatever you want. Correct equals torch dot equal. So we have a function called EQ. This function compares between two tensors and returns whether there were matches between the yTrue and the yPred. It will return true, and then and if there were no matches, it will return false. So if we have, just for example, if you have a tensor, say my tensor A equals torch.tensor, and then we pass in 1, 2, 3, 4. And then if you have my tensor B equals torch.tensor, and then pass, for example, 10 to 44, for example. Now, if we use torch.equal function and then pass in here my tensor A and then pass in here my tensor B, it's going to compare between these two tensors. As you can see, we have true, 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 true. So does one, but because we haven't specified that as here, dot all. We have mixed up the variable names, so I have to pass in my tensor B. Yeah, false, true, false, true. Yeah, that's right. 1 doesn't equal to 10. Well, that's false. 2 does equal to 10. equal to 2. So we have true in here. So if these elements, if these corresponding elements match up, it will return true. If these elements don't match up, it will return false. It's just an important function in Pytorch. It's a fundamental function in Pytorch. So 1 doesn't equal 10, okay, false. 2 does equal to 2, true. 3 doesn't equal 40, that's false. And 4 equal to 4, that's true. And then we have to pass in y true, comma, y pred. And then in order to get the sum of this tensor, we need to call the sum. So sum just sums up all the true elements. How many matches do I have? 2. Well, I have 2 elements matching up. 2 matches up with 2, 4 matches up with 4. And then we need to call dot sum and then dot item. Item is a magical function that returns the number, just the number of the tensor. Dot item. That's 2, as you can see in here. And then we need to divide the number of correct samples by the total. So accuracy equals correct, the number of correct samples divided by the length of y pred, divided by the length of y pred, and then we need to multiply it by 100. Because it's an accuracy, we need to multiply it by 100. So dividing the number of correct samples by the total number of samples, including true negative, true positive, false negative, false positive, we will get the accuracy, as the accuracy equation states that if we need to calculate the accuracy, we need to pass in here the number of correct predictions over all predictions, or we need to divide the true positive plus true negative by the total of these true positive, true negative, false positive plus false negative. And that's an important accuracy. Accuracy is a straightforward metric that all ML engineers have some intuition about it. And then return accuracy as a measure. Run this. Well, I think now we've got all the pieces of the puzzle that makes us ready to build a training loop. So let's now go ahead and build a training loop. Well, now if you want to build a training loop, we need to put a comment in here, creating a function to time our experiments. Well, is this important? Yes, it's important. Why? Because in modern machine learning and deep learning projects, we have a trade-off. We have a trade-off between the model's performance and the time or how fast it runs. So we need to put in mind these two aspects: the model's performance versus how fast it runs. Because sometimes you need a very performant model, but you don't care about speed. You don't care about how fast it runs, especially in hospitals. When you build a model for a hospital, you don't care for the time aspect compared to the correctness or the accuracy of the model's results. While in some financial systems, for example, fraud detection, cards, fraud detect or not fraud, you care about the fastness or the speediness of the classifying. So that you have to keep in mind these aspects. So machine learning is very experimental, and you're gonna face a lot of situations. Every project differs from the previous project. Two of the main things you have to convert into Markdown. You will often track are: 1, the model's performance. So the performance of the model, loss and accuracy. So what is the loss? The loss should be lower The lower the loss, the better the model. The higher the accuracy, the better the model. And 2, how fast it runs. So with that being said, let's create this function. So we have a very important library in Python called timer. So from timer, import default timer as timer. So timer is a very useful library in Python. So shout out to their authors. It's a very useful library to get the time of the specific starting of the model training and then the specific ending of the model training. So we need to get the start point, the time when the model starts to train, and then the time when the model ends to train. The time when the model ends to train. So here, def print train time. This function takes from its start as flow and end as flow, and then device, because you can run this model on 2 different devices. You can run it on a CPU or on the GPU. If you change the runtime type, you could choose GPU. But now I'm gonna keep it simple. Well, our dataset is not that big dataset, and our model is not that big of a network, so we can use device CPU. So device as torch.device, I'm gonna keep it none. Then prints, this function prints difference, the difference between start and end time. And then total time equals end minus start. So this is a simple equation. End, the time when the model ends training, minus the time when the model started training, and then we will get the total time. Okay, return total time. We could also print some message in here. Train time on this device, could be GPU, could be CPU, could be CUDA enabled device, whatever you have chosen. And then total time 0.3 fractions. We want just 3 decimal fractions of the time, and then seconds. So we're gonna measure this in seconds. Okay, so now let's go ahead and build this, or let's try this function out. So start time equals timer, and then some code goes into here, and then end time equals timer. So this timer is nothing but a function we have imported from timer. Import default timer is a function. Okay. And then if you want to use our function, print train time, and then pass in here the start as start time, the end as end time, and then as the device as CPU. Let's go ahead. Well, now train time on CPU is 0 seconds. So when you put a comment, the comment takes to run 0 seconds because it's nothing, just a comment. And then you'll notice that the total time that this comment took to run between the start and the end to finish executing or interpreting this comment is this very small number. It's 3.21 times 10 raised to the power of -5. So it's a very small number. Okay, nothing. And then we need to get another. So now we have gotten all the functionalities to be able to train the model. So let's go ahead and 3.3 creating a training loop and testing loop. So in Pytorch we call it loop. So the training loop and testing loop to train and training the model on batches of data. So this is a very good explanation. Creating a training loop and testing loop and training the model on batches of data. First of all, we need to create some progress bar. So we have this library from tqdm.auto import TQDM. If you search this up, TQDM, what is TQDM library? What is TQDM library? This library, the author of it is a Spanish programmer, and he named it as TQDM, derives from the Arabic word تقدم أو تقدم. So this library is called TQDM. The creator of it is a Spanish programmer, and he derived the name of this library from the Arabic word تقدم, which can mean progress. And it is an abbreviation in Spanish for the same thing. So if you go ahead from tqdm.auto import tqdm and then set the seed, we're gonna set the seed and start the timer. So torch.manual seed 42, and then we're gonna start the timer to count the time. So train time start on CPU equals timer function, and then set the number of epochs. Epochs equals 3. So I'm going to keep it simple, and I'm going to keep it small in order to fit in this video. So the number of epochs could be higher, could be 10, could be 11, could be whatever you want. So we have faced in this project 3 main and significant hyperparameters. The first one being the batch size, the second learning rate, the third epochs. So batch size 32, learning rate 0.01, epochs 3. These are all hyperparameters that you as a machine learning engineer or as a DL engineer should optimize, should find the best values that gives you the best and highest results, gives you the lowest loss and the highest accuracy. And then here create a training loop. We're gonna create this training loop. So for each epoch in TQDM, this library TQDM, and then pass in here range and then pass epochs. This library will take care of the progress of the range and then increase the progress and progresses or pushes up the progress bar forward. The first thing we need to do is print the number of epoch. You don't have to, but it's just to inform you, kind of gives you a feedback to sort of where the model reached up. So model epoch and then epoch \n to put a new line, and then dash 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 dash, 6 dashes there, and then training. Let's start training. So notice in here this is an important thing in Pytorch. When you train a computer vision model in Pytorch, it's a little bit different from the regression or classification, because you need to create an insider for loop inside this outer for. So you have to create an inner for inside this for. This for loop loops through the epochs, but this for loop loops through the batches. So for each batch for each batch, comma X, so the images, comma Y labels in train data loader. Now I want you to have a think in here that if you used train dataset, it will result in an error. If you use train data, it will result in an error. We don't want to loop through this dataset. This is a static dataset, but we have created a data loader over this dataset called train data loader. This data loader contains the batches. So if you pass this to a next here, you will get if you pass this to an iter and then next, you will get a batch. You will get a batch, 32 images in here and 32 labels. So the model will process a batch each time. Each time the model will look at 32 images and then updates its weights, updates its internal representations, updates its internal configurations in order to better represent the data, in order to better fit the data. So we have 32 images and their associated labels over here. So each time we're gonna loop through this train data loader, and we have to pass this to a function called enumerate to get the number of the batch. So batch, this variable will contain the number of the batch. We have 1875 batches. In other words, 1875 batches, and each batch contains 32 images and 32 labels. Now we have created this inner for loop. The first thing we need to do is, of course, set the mode of the model as train. So model.train function. This train function is simple. It just sets the module in training mode. It's nothing other than that. It's just set the module in training mode. And then the first thing, forward pass. So always when you train a model, you have to pass some data in. So we have to pass the data through the network. We have to pass the data through the network. Like in here, we have to pass the data through the network. We have to pass it forwardly. So pass the images forward. Goes in a forward manner. Just goes in a forward manner. Okay? Forward propagation. Forward pass. So here, forward pass, Y pred, and then use the model and then pass X. We're going to pass these X's, these features, these images. We're gonna pass these images, specifically 32 images, through the model forwardly in a forward manner, and then the model will produce some outputs, and then we'll store those logits. The model will store those logits, will keep those logits in this variable ypred. So that's how simple it is to do a forward pass. It's just the model being as a function. Model, and then open parentheses, and then pass the x's, pass the x, pass the images. 2, once the model has seen the images and has produced some outputs, we need to calculate the loss. Calculate loss. Loss per batch. Notice this loss will be per batch. Then we need to normalize this loss. We need to scale this loss in order to be a considerable loss, because after finishing this for loop, it will have a very high loss, because it will add up these losses accumulatively in an accumulative manner. So loss equals loss function, and then pass in here ypred. We're going to compare the y predictions, the predictions of the model. We're going to compare them to what? To the ground truth labels, to the real labels, y. So this loss function is what? Is just cross entropy. As you can see in here, it's cross entropy loss. It will calculate how much difference between the predictions and the true labels. And then we need, sorry, I have forgotten to create a variable here called train loss. This variable is significant and important. Why? Because this variable will contain the accumulated losses over time. Because this loss will be updated each batch. So each batch will calculate the loss per batch and then overwrite this loss. But this variable will keep track of the whole loss, of the entire loss across all batches. And then we will divide this very high loss by the number of batches to normalize the loss. So train loss plus equals, so accumulatively, place loss equals loss. That's how easy it is. So accumulatively increase the loss. 3, optimizer 0 grad. So optimizer dot 0 gradient, important step in training. And then 4, loss backward. We're gonna have to do the back propagation algorithm. So loss backward. So back propagation algorithm. Loss dot backward. And then 5, gradient descent. We're gonna implement gradient descent using optimizer dot step. And then print out what's happening. We're gonna print out what's happening as a feedback to see how the model is going through training. So print out what's happening. If batch, now notice how many batches do we have? We have 1800, so 1800 batches. So if you try to print out all these results, it would be a very long output. But we need to cut it up. So if batch is divisible by 400, meaning every 400 batch, we're gonna print out some feedback to give us some insights about the model's performance. So if you go into here, looked at batch. So batch is the number, the batch number, whether it was 50, 70, 200 until 1000 and 800. So this represents the batch number, and then we will multiply it by the length of x. Now a clever question here, what is the length of x? Well, x is a batch, so the length of a batch is 32 samples, 32 examples, 32 images. Out of, so this the model after 400 batches will be have looked at. So looked at batch times length of x out of the total number of images. So here length of train data loader dot dataset samples. Okay, so this is kind of a feedback to us to inform us some information when training. And then divide, we need to divide, normalize, you could call it scale the train loss by length of train data loader. So because now we have increased the losses accumulatively, we will have a very high loss that doesn't represent the real loss of the model. So we need to normalize it, we need to scale it to get a real representation, to get a real view of the loss. So train loss divide by the number of batches. So how many batches do we have here? Length of train data loader. We have 1875 batches. So we need to divide the loss by this number, length of train data loader. That's how easy to normalize a loss value. Then lastly, testing. This is the training loop, but we need to create another loop for testing. So testing, we need first of all to set the model status to eval. So model.eval, what eval does, set the module in evaluation mode. So rather than training mode, now in evaluation mode. This is not an important step, but it is a best practice. Why? Because eval turns off some training related algorithms like back propagation and gradient descent. These algorithms will only work when the model needs to optimize the parameters. In other words, when the model trains. But in testing, we need to turn off these algorithms to not to take off far more space in the memory, and also to not make the model busy with these algorithms. And then with torch.inference mode, also inference mode turns off all training related work and enables, as you can see here, it's a context manager. Why? Because in Python everything starts with the with keyword. Consider it a context manager. So it is a context manager that enables or disables inference mode. If you search this up quickly in here, inference mode, this is a function, inference mode Pytorch. This is a function in Pytorch documentation, context manager that enables or disables inference mode. That's very nice. So if you read in here, inference mode is a context manager analogous to nograd. Well, previously it was called nograd. Nograd is an abbreviation to no gradient. But now it's called inference mode, meaning the mode of inferencing, of predicting, and to be used when you are certain your operations will have no interactions with autograd. For example, model training. Code run under this mode gets better performance by disabling view tracking and version counter bumps. Note that unlike some other mechanisms, that locally enable or disable grad. Entering inference mode also disables forward mode. Well, that's a very insightful message. So now in here, we need to create a loop for X test. Notice in here, we don't need to create a batch. We will just stick to X test, comma Y test for each testing images and for each testing labels in the test data loader. We will do the following. The first thing, forward pass. So forward pass. And then we will calculate the test spread. So the model will output test predictions equals model and then pass X test in here. And then we will do the second step, which is calculate loss. Notice in here, calculate loss. Test loss plus equals. We will do this in a one step now rather than splitting it in two steps. We will accumulate on the test loss. So why don't we create a test loss variable here? Test loss, comma test accuracy equals, and initialize these with 0, 0. So we're gonna initialize these variables with 0, 0, and increasingly, gradually, we will increase the loss by the amount of loss function that will compare between the test predictions and the ground truth labels. Y test. And then the third step is calculate accuracy. We're going to calculate accuracy in the testing step. So test accuracy equals plus equals accumulatively the accuracy function that we have created above. I think I have called accuracy. Yeah, here we have called it accuracy. Yeah, we may have called it accuracy function. Now accuracy function, and compare between the Y true, which is in this case the Y test, represents the ground truth, the real labels, the truth labels, and compare it to the Y pred, which are the predictions of the model of the forward pass. So we need to pass in here the test pred. Now, with that being said, I can say that we have done from this for loop of the testing batch. But now, as we have normalized the train loss, we just need a final step to normalize the test loss. So normalize, scale the test loss average per batch. So we need to get the average, the mean of the loss and the mean of accuracy. Otherwise, it will be a very high numbers, very huge numbers. So test loss and then divide by equals length of test data loader, and then test accuracy equals, or divide by equals. So we want to divide the accuracy by the length of test data loader. Why? To normalize these loss and accuracy values. So normalize or scale, normalize or calculate the test loss average per batch, the test loss average per batch, and the same thing in here, normalize or scale the test accuracy average per batch. The last thing we need to print out what's happening. So print f string, we will print \n to go to a new line. Train loss, so the loss computed on the training set is train loss, and we're gonna shorten it to just 4 decimal places, and then we're gonna put a pipe and then test loss as test loss, and then we're gonna shorten it to 4 decimal places, comma test accuracy as this variable here, test accuracy, and then we're gonna shorten it to 4 decimal places. Now we have done the testing batch or the testing loop. The last 2 steps are to end or to calculate the time when the model ends the training. So train time end on CPU equals timer. I think I've called that variable here something like that. Train time start on CPU. Yeah, So we have train time start on CPU and then the timer function. So this function will count or will get the time before training the model, and this function here will get the time when the model has finished up training. And then we will use that function, that magical function that we have created above, total train time model 0. So the total time, or we can call it model, the total train time. So the total training time that the model took to train the data. So how long does the model took to train? Equals print train time and then pass in here start as start time or train time. Train time start on CPU, comma, and equals train time end, train time end on CPU. Very long variable names, and then device equals string function, and then pass in here next, and then pass in here model dot parameters dot device. Well, this might seems like a little bit tricky, but it's so simple. We have a model. This model has some parameters. These parameters are, we can get the next of it, so we can pass this to a next. We will get some parameters. These parameters are living on the CPU. Dot device, we get CPU. If you pass this all to a string function, we will get CPU. So this code in here is does the same operations in here. CPU, because it gives me the name of the device, that the parameter of the model, the name of the device. So we need to pass to the device parameter the string function, and then pass next to the string function, and then pass to next the model.parameters method. This code will result in the device name that the model's parameters are living on. Now, if we try to train this model, 3, 2, 1, train. Okay, that's really nice. It's now training. As you can see in here, epoch 0, and then the model looked at this amount of images. Whoops, we've got an error. Now, what does this error say? Runtime error. The size of a tensor of tensor A, 32, must match the size of tensor B, 10, at non-singleton dimension 1. So this error indicates that we have a shape mismatch, that we have a shape error. And we know that in machine learning, shape errors are one of the most common errors in the world of machine learning and deep learning. To solve this error, all we need to do is we need to call the argmax function on the test predictions that are coming from the model, and then specify dimension as 1. Now let's try again. Let's train this model again. 3, 2, 1, train. Hopefully this time the model trains successfully. And now epoch 0 looked at 0 images out of 60,000. As you can see here, the model is processing the images. Now we haven't gotten that error again, which means we have solved that error. As you can see in here, the train loss is 0.49, and the test loss is 0.49, and the test accuracy is 82%, which is nice. And then epoch 1, or the next epoch, we have train loss of 0.49, we have test loss of 0.48, and test accuracy of 83.70%. And as you can notice in here, the train loss 0.47, test loss 0.53, and test accuracy 81.36%. Train time on CPU, the model took 34.66 seconds to train on the full training set. Now we have trained the model successfully. As you can see in here, the progress bar is now 100%. The model took 34 seconds to train. What about now we create some predictions, that we can create a function to predict with the model. So in order to create a function to predict using the model, we need to create a function called make predictions, def, and then we call it make predictions. To make some predictions, we need to pass in here model this model as torch.nn.module, and then pass data, which is a list of data, and then we need to pass in here devices or device as torch.device as equals device. Now we don't have this device variable, so let's create this device variable. Device equals, now we're gonna make this device agnostic code. In Pytorch we have something called device agnostic code. So we're gonna choose CUDA if torch.CUDA.is available, else we're gonna use our normal CPU. So now currently you can infer that we have CPU, so this device variable will contain the CPU string. So if we have GPU available, if torch, so this is a dynamic code. If we have, if torch.CUDA.is available is currently available, meaning we have GPU running, then it will be CUDA. If not, we will have CPU. Okay, that's called device agnostic code, making the device dynamic based on what you have available. And then prediction underscore props, meaning the prediction probabilities, equals a list, an empty list. We're gonna create an empty list, and then model.to, we're gonna move our model or transfer our model to the device, whether it was GPU on CUDA or whether it was CPU. And then we're gonna set the mode of the model as evaluation. So set the module in evaluation mode by using the eval function, model.eval. And then with torch.inference mode, we're gonna enable the inference mode using this function, inference mode. First of all, prepare the sample. We're going to prepare the sample, add a batch dimension. We're going to add a batch dimension and pass to target device. So sample, we're going to create a variable called sample equals torch.unsqueeze function, unsqueeze, and then pass sample. We're going to pass sample in here, comma, dimension equals 0, dot to device. Well, before we create this code, we need to loop through the list of data. So we're going to say for sample in list and data, and then we need to indent this code. So for each sample in data, we're going to create a variable or override this variable sample to equal torch.unsqueeze, and then pass sample and add the batch dimension on the 0th dimension. Dimension equals 0. And then we're going to send this sample to the device, to the target device. Forward pass, and then model predicts or outputs raw logits. As we said before, the model always outputs raw logits. So pred logit equals model and then pass sample. We're going to pass this sample through the model, and then the model will produce outputs, will produce logits. And then we're going to store these logits in this variable pred logit. The next step is get prediction probability. Get prediction probabilities or probability. Get prediction probability. So turn logit, we're going to convert logit into prediction probabilities. So pred prop equals torch.softmax. We're going to use the softmax function. If we read about softmax function in here, softmax in, for example, Wikipedia, it will say the softmax function, also known as softargmax or normalized exponential function, converts a vector of k real numbers into a probability distribution. So it converts a vector of k real numbers, in other words, logits, into a probability distribution of k possible outcomes. So that's very nice. Let's go back in here, torch to softmax, and then pass pred logit dot squeeze function. We need to squeeze it. Dimension equals 0. The third step is get prediction probability of the GPU for further calculations. We're going to get the prediction probabilities of the GPU. So pred underscore props dot append and then pass prediction probability dot CPU. So we're going to downgrade the prediction probabilities from the GPU to the CPU by using this CPU function, and then we're going to append it to the pred props list. As you can see in here, this is an empty list called pred props. We're going to append the value of this prediction probability to this list pred props. And then lastly, we have to return torch.stack. So we need to stack these prediction probabilities. If we try to run this function, okay, now let's use this function and make some predictions using the model. So what we need to do now is import random and then random.seed. Let's make the seed 42. Test samples. Now we want to loop through the samples and then pick some test samples, and then test labels equals empty list. So we're going to initialize the test samples variable as empty list and test labels variable as empty list. So test labels okay, equals empty list. For sample comma label, for each sample comma label in random dot, we're going to sample from the list of test data. So if we convert our test data, which is our dataset, FashionMnist dataset, if we wrap it in a list function like that, we will get, as you can see in here, it's loading. We will get a huge list that contains all of the test data, a huge and massive list. As you can see here, dot dot dot, because it can't show all the samples, so we're going to loop through this list, okay, to pick a random sample first, and then loop through this random sample, and this sample will contain k equals 9. We will pick 9 samples from this huge list of test data. Test samples equals dot append and then pass sample, and then test labels dot append, and then we're going to append the label. Here we are appending the sample to the test samples list and appending the label to the test labels list. View the first sample shape. If you now try to view test samples, which is this list now after this for loop will contain 9 samples, this list, and we need to show the shape of the first element. Notice we have an image of 1 color channel, 28 height and 28 width. So we have this dimensionality for an image, meaning we have successfully looped through the test samples and picked 9 samples and then appended them to the test samples list and test labels list. Test samples, if you try to view the test samples, it's considered a list that contains 9 samples. If we try to go to the up here, we have a list of tensor, and each tensor represents an image. If you get the length of this list will be 9. So you have 9 samples. And then test samples, if you get the first element of this list, it will be a tensor, a single tensor for a single image, and if you get the shape of it will be 1 color channel 28 28. And if you want to visualize this image, all we need to do is just squeeze this image dot squeeze, and then pass it to plt.imshow function in matplotlib. It will be just a normal image like that. And just to show it in grayscale mode, set the CMap equals to gray. Now, what we need to do is we need to create some predictions using the function that we have created earlier on these test samples. So make predictions, let's put a comment, make predictions, pred props equals make underscore predictions. This function that we have created earlier takes from me a model. So model equals model, our model that we have created earlier, and then data equals that list that is called test samples. View first two predictions probabilities. Now, if you wanted to view the first two prediction probabilities, it will be as follows. Pred props show me the first two. These are the first two prediction probabilities. Each prediction probability contains 10 logits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 probabilities. One probability for each class. And then the next sample, the same. The model thinks that it is a t-shirt, this probability. The model thinks that it is a trouser by this amount of probability. And so on, so on. So these are probabilities that represents how much confidence the model thinks that this image relates to a specific class. If you move on to the next thing, now how do we convert these probabilities into labels? Well, to convert them, we need to do the following step. Convert prediction probabilities into labels. And to do so, we might pass these probabilities into the softmax, and then we will get probabilities, and then apply the argmax, or we could take in the logits and then pass them to the argmax function. Both ways will work. So if you wanted to do this operation by using the argmax prediction underscore classes to convert these probabilities into classes equals pred underscore props dot argmax and then pass dimension equals 1. This argmax function will convert these probabilities into labels. Now, if you show these labels, what are the pred classes? Are as follows. So 5, 3, 8, 4, 3, 0, 4, 7, 1. These are the labels, the targets. We have generated it from using the argmax function. So the highest argmax, what argmax function does is that it gives me, or it returns the index of the highest probability. So the highest probability in this situation, it's in the fifth index. If you count in here, 0, 1, 2, 3, 4, 5. So this is the highest probability. And then the argmax function returns the index of the highest probability. All it does, argmax, just returns the index of the highest probability or of the highest element. Now, if you want to plot it in a figure, we need to use the following functionality. First of all, plot predictions. So plt.figure, and then pass in here fig size equals 9 by 9. We're going to specify the fig size as 9 by 9, and then n rows, number of rows equals 3, and n columns equals 3. For I, comma, sample in enumerate, and then pass test samples. So we're going to pass the test samples, this list that we have created above, we're going to pass it to enumerate, and then for each I, the index of the element, comma, sample of the element, and enumerate test samples. We're going to do the following steps. First of all, create subplot to append it to the plot. So plt.subplot, and then pass in here n rows, comma, n columns, and then I plus 1. So subplot just adds subplots to the figure. We have a whole figure, and then we need to create or add subplots to this figure. So we need to specify the number of rows as 3, number of columns as 3, and then I plus 1. Secondly, plot the target image. Well, to plot the target image, as we discussed before, plt.imShow function, and then pass the sample.squeeze. We have to squeeze the image because these images are grayscale. They have just one color channel, and Matplotlib expects grayscale images of the shape just height and width, so it doesn't expect to be or to have a color channel. So we need to squeeze the image to get rid of that color channel. Comma, CMap, the color map equals gray, to make the image show in grayscale mode. Find the prediction. Now we need to find the prediction in text form, in the text form. For example, sandal or t-shirt, rather than being in a numerical format. So pred underscore label equals class names. So we have a list called class names. If you show this list, class underscore names, it will be a list of all the classes and labels that we have in text form. Class names, and then index on the pred underscore classes, and then we need to choose or index on the I. And then thirdly, get the truth label in text form, also in text form. Truth underscore label equals, so this is the predicted label. The model predicted, for example, that this image relates to a shirt, but in reality it might relate to a different label. So truth label equals class names, and then get the test underscore labels, which are the true labels. If you show this test labels, it's just a list that contains all the labels of 9 elements, 5, 1, 7, 4, 0, 4, 7, and so on. So test labels, and then get the item at the index I. And then we need to create a title. Create a title for this plot, for the plot. So title text, the text of the title, equals f-string prediction or pred underscore label, what the model has predicted, and we'll put a pipe, and then truth. The truth is the truth label. So this will be the title of the plot. Pred means prediction, and then we will plot here the pred label, pipe truth, and then we will plug in here truth label. Check for equality. Now we need to create an if condition to check for equality, whether the prediction matches the truth label. If it matches up, then we will color it in green. If they don't match, we will color them in red. So check for equality, pred between prediction and truth, and we're going to change the color of title text. So if pred label equals truth label, well then that's nice, the prediction matches the truth. We need to plt.title to set the title function of the plot to be as title text as this text, and then so title text, the name of this variable, comma, and then we will set the font size as 10 to be in font size 10, comma, color equals green. Else plt.title, and then pass title text, comma, font size equals 10, comma, we're going to set the color as red. Lastly, plt.axis false. We don't want the axes to show up. Now all we have to do is just run the cell. So let's run the cell. As you can see, we have a figure that contains 9 samples. For example, this sample the model predicted it's sandal and truth is in fact sandal. So the model has got it right, and that's why we have colored it in green. But this, as you can see, prediction dress, but in truth it's a trouser. So the model has got it wrong, and so on, so on. As you can see in here, this is true, predicted coat, truth coat, predicted sneaker and truth sneaker, and prediction is coat, truth coat, prediction dress, truth dress, and so on and so on. If you wanted to get some other samples, all you have to do is just run this. We have to close this seed or turn off the seed and then run these cells again. You will notice that we will get different samples. For example, the model has predicted that this is a bag, but in reality or truth it's an ankle boot. Predicted sneaker, truth sneaker. This is right. Now I want you to have a think. Why do the model have these things mixed up? So the model predicted that this is a bag, but in truth it's a sandal. Well, because the model is confused. It's confused because these shapes are too complex for the model to detect the difference between the truth label and between some other overlapping labels. So why don't we visualize a confusion matrix that will show us how much confusion the model have in terms of these overlapping labels. So let's put a comment in here. Let's name it making a confusion matrix for further prediction evaluation. Making confusion matrix for further prediction evaluation. Well, a confusion matrix is a fantastic way of evaluating your classification models visually. So let's write this in here. A confusion matrix is a fantastic way to visualize your classification models performance. So a confusion matrix is a fantastic way to visualize your classification model performance, and we have to make a confusion matrix using torch metrics. So we're going to use torch metrics library, torch metrics dot confusion matrix. 3. Plot the confusion matrix using, we're going to use this library mlextend dot plot confusion matrix. Let's put this in number 1. So as we said before, a confusion matrix is a fantastic way to visualize your classification model performance. Make a confusion matrix using torch metrics dot confusion matrix class, and then plot the confusion matrix using mlextend dot plot confusion matrix. So let's do these steps right now. First of all, we need to make predictions over all the test data samples. So import tqdm.auto. So from tqdm.auto import tqdm. 1. Make predictions with our trained model. We're going to make predictions with our trained model on the test dataset, on the test dataset. So the first step is to create a variable called ypreds equals a list, and then model.eval. We're going to set the module in evaluation mode, .eval with torch.inference mode. Always when you want to make predictions or to use the model in inferencing or for inferencing, you have to turn these two things on. Model.eval and then with torch.inference mode function to turn the inference mode on. For x comma y, for each x and y in tqdm, and then pass in here test data loader, comma, we're going to pass a description as making predictions dot 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 dot, and then send the data to the device and targets to target device. X comma y equals x dot to device. We're going to send the x to the target device, comma y dot to device. So this code just sends the data x and y, features and labels, send them to the target device, whether it was GPU or CPU, depends on what you have available. In this case, we have CPU. Secondly, do the forward pass. So we need to do the forward pass. Y underscore load equals model and then pass x. So we need to pass x to the model, and then the model will make some preds and then store it in y loaded variable. Turn prediction from loaded. We need to convert the predictions from loaded form into prediction probabilities and then into prediction labels. So how to convert the loadeds into pred props into prediction labels? Well, we have discussed that before using softmax function and then using argmax function. So y underscore pred equals torch.softmax. So we need to use the softmax function, softmax activation function, to convert the loadeds into prediction probabilities, and then we need to convert those prediction probabilities into prediction labels. Y underscore loaded dot squeeze. We need to squeeze the loadeds and then specify the dimension as 1. And then once we have applied the softmax activation function on the loadeds to convert the loadeds into prediction probabilities, we need to call argmax, and this time we have to pass dimension as 1. Well, the softmax differs from the argmax that we have to pass dimension here as 0. So we have to specify the dim as 0 for softmax, but the dimension as 1 for the argmax. That is the difference between the two functions. Now put predictions. We need to put predictions on CPU for evaluation. So ypreds dot append and then pass ypred. This is the ypred, and then we need to call dot CPU function on it. Now the next step is to concatenate list of predictions into a tensor. So to make this, to concatenate list of predictions into a tensor. Print ypred. We're going to print ypred just to show the predictions, and then y underscore pred underscore tensor equals torch.cat. So cat function is used to concatenate list of predictions into a tensor, and then we need to pass in here y underscore preds. So ypred underscore tensor is as follows. Show me the first 10. Now if you run this cell, we have forgotten the colon, a classic error, no problem. Now let's run again. We have another error, expected an indented block for statement. Yeah, we haven't indented this code. So we are fixing or debugging the issues on the fly here. What a wonderful lesson this. And then now if you can see, these are all of the predictions that we have made. So now we have passed all of this data through the model, and the model made predictions on these samples. As you can see, these are the different samples, and these tensors represents the predictions of the model. The next step is just to show up a confusion matrix. Now you might have the question why we have made all these predictions. Well, a confusion matrix shows a comprehensive map that shows how the model has confused on all of its predictions. So we need to predict, in other words, make predictions, and then we can visualize the confusion matrix. So import mlextend, import the library mlextend, like that. And then if you can check the version, we need this version of mlextend. So if you want to use mlextend to plot a confusion matrix, you need at minimum this version, 0.23.4. And then let's just go ahead and try to import Torch metrics. So Torch metrics, I believe that Torch metrics is not embedded in Colab. If you try to import Torch metrics like that, will give you an error, because until now Torch metrics is not being appended in Colab. So you have to install like that, pip install Torch metrics. Now it will download this library, Torch metrics. Torch metrics is a wonderful library or package that contains a lot of the metrics to evaluate your models. As you can see here, welcome to Torch metrics. Torch metrics is a collection of 100 plus Pytorch metrics implementations and an easy to use API to create custom metrics. It offers a standardized interface to increase reproducibility, reduces boilerplate, distributed training compatible, rigorously tested, automatic accumulation over batches, automatic synchronization between multiple devices. So Torch metrics is a library that contains a lot of different metrics for across many domains. As you can see in here, we have for aggregation these metrics, we have for audio these metrics, we have for classification these metrics, and so on and so on. We have for clustering, detection, image, multimodal, nominal, pairwise, regression, and a lot of other domains that all have metrics in this library, Torch metrics. So if you go back in here and try to run this, as you can notice in here, successfully installed this Torch metrics. Once it installed this library, we can import it in Google Colab environment, and then we can use Torch metrics to compute the confusion matrix. As you can see in here, successfully and installed NVIDIA CUDA DNN in order for this library to work in our environment. Okay, so now it has successfully installed Lightning utilities for this library. Now import Torch metrics. It will work as all other libraries. Now it's trying to import this Torch metrics library, and then the next step is to compute this conf matrix. So all we need to do here is from Torch metrics import the class. We need to import the class confusion matrix, and then from mlextend.plotting import plot underscore confusion underscore matrix. We need to use this class to first compute the confusion matrix. This class is coming from Torch metrics library. So from Torch metrics import confusion matrix, and then from mlextend.plotting import plot confusion matrix. If you search about confusion matrix in Torch metrics, we will get a documentation about how to create a confusion matrix using Torch metrics library. You can see in here all the codes and explanations to create confusion matrices using the package Torch matrix. So let's try to create a one for this dataset. Step 1, set up confusion matrix instance and compare between predictions. We need to compare between predictions and targets. In other words, labels. So confmat, short for confusion matrix, equals confusion matrix class, and then pass num classes. How many classes do we have? Well, we have 10 classes. We are classifying into 10 classes, and then task is multi-class. Confmat underscore tensor, we need to pass in it a tensor, so we're going to use confusion matrix and then pass in here preds equals our y pred tensor that we have created above, and then target equals test data dot targets. Why? As we have discussed in the beginning of this lesson, that test underscore data is a dataset, FashionMnist dataset, and then if you access the targets attribute, we will get a long tensor that contains all of the targets for these samples. And then lastly, plot the confusion matrix. So plot the confusion matrix. Well, to plot the confusion matrix, we're going to create a figure, comma axes equals plot confusion matrix. We're going to use this function, plot confusion matrix, and then pass confusion matrix that we have computed here. So equals confusion underscore matrix underscore tensor dot numpy. We need to turn it to numpy version, comma class names. The class names equals class names. Class names is a variable that we have created above. It's just a list of all the class names, as you can see in here. And then lastly, we have to pass in here fixed size equals 10,7. Now if you run this cell, we will get a pretty confusion matrix that shows up the predictions versus labels. So as you can see in here, t-shirt or top with, for example, it's corresponding in here, t-shirt top is being the most 332. Here the diagonal represents the true or the true predictions that the model has made. As you can see in here, we have the most values lying up in this diagonal, whereas these values are in the upper here, or in the here below this diagonal, we have very small rates of values, and that indicates that the model is considerably good. So coat with, for example, shirt, we have 394 samples. The model has mixed up between the class coat and the class shirt. So this class is confusing for the model to differentiate between coat and shirt. And also you can notice in here that the model has confused between shirt and t-shirt. We have here 216 samples. The model has confused between detecting whether this image contains a shirt or t-shirt, and so on and so on. So this is a confusion matrix that shows up the values or the confusion between labels. So in this lesson, we have created a model that modeled the dataset of FashionMnist and created some predictions and visualized them. So we have prepared the dataset. First of all, we have imported the necessary libraries, as you can see in here, and then we have gotten a dataset using this FashionMnist class, and then we have inspected the data using the length function and also visualized some samples of the data, and then visualized a bunch of images. And then fourthly, we have prepared a data loader that converted our dataset into batches. And then we have created a model using Pytorch library. As you can see in here, we have created a model and then specified this architecture of one flattened layer and then two linear layers, and instantiated a new object of the model. And then we have trained the model. As you can see in here, we have set the train time using the train time function, and we have also prepared this TQDM for our progress bar and a lot of things. And you can see in here we have made predictions and evaluated them using a plot like this to view the correctness or wrong of the model predictions. And then lastly, we have made a confusion matrix that shows the confusion of the model. So I hope I meet you at other lessons and other tutorials. For the time being, thank you and goodbye.